So in this exam style question, they start off by telling us that a K- meson has a strangeness of -1. Then they just want us to state the quark composition of a meson in general. And we know that a quark, by this time we know that a meson is made of a quark and an antiquark. And we've given that answer a few times now. Then they'd like us to state the baryon number of the K- meson. Well, we also remember that each quark has a baryon number of +1/3, and each antiquark has a baryon number of -1/3. So therefore any meson has a baryon number of 0. Then they would like us to state the quark composition of the K- meson. So we know that it's got a strangeness of -1, so it must have a strange quark in it. That's a given. And so we know it's got a strange quark in it, and then we know that it's got a charge of -1. And again, we go back to our table on quarks, remembering that a particle with a strangeness of -1 must have a strange quark. Therefore, it must have either an up quark or it must have an anti-up quark or an anti-down quark involved. And if you want it to have a negative charge, you better have the anti-up quark, because the anti-down quark is positive charge. So it must be an anti-up quark. So it's a strange quark and an anti-up quark. So strange anti-up is the quark composition of the K- meson, and that's all they wanted. That's all they wanted you to write. So now we're back to a Feynman diagram. We haven't seen one of these for a while. The diagram below shows a Feynman diagram for a possible decay of the strange quark. So here we started with our strange quark. That's decaying by the weak interaction into an electron antineutrino, and a up quark. Remember, I don't think we've actually seen a Feynman diagram specifically for quarks before, but this is something we will actually see sometimes. It's not going to be uncommon to see this kind of thing. Instead of the standard proton decaying into a neutron or neutron decaying into a proton, whatever, we will see something like this. So which interaction is responsible for this decay? And it's very clearly the weak interaction. We can see that in many ways from this W- boson involved. That's clearly that is the virtual exchange particle for the weak interaction, along with the W+ boson. Or we simply see that it's a strange quark decaying into a non-strange particle. This has S equals -1. This has S equals 0. Therefore, we must have that. It is the weak interaction. So after that, energy and momentum are conserved when the W- particle is produced. State two other quantities that are also conserved and one that is not. So let's go up to looking at the W- particle. We know, for instance, that charge is always conserved. And we can see that clearly is the case here. This W-, when this W- is created, this has a charge of -1. Strange quark had a charge of -1/3.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.